All right, so here is that same geometric pattern. We've removed all the circles on the circumference or the perimeter of the outside circle, which just want to confirm has a radius of square root of 108.4 dec, not dec 4. Okay, so we're looking at this perfectly symmetrical geometric pattern. Essentially, we've created, again, a polygon with 24 sides. These are the 24 sides with the lengths of point dec root 2. It's anchored on the line, on the points that are sort of around the 45-degree line. This point is defined by this point has the coordinates of 3.2 and 3.2. And this point has specific lattice points, this one specific lattice points. So this geometric pattern is anchored on the base 12 Cartesian plane, very specific and precise lattice points which define its structure. So we have a triangle in here then. So we have a 24-sided polygon. So we have 28 triangles. We can divide each of these triangles in half, each of these sections of the polygon in half. So we have these little triangles with the base of 3.2 root 2, then the short side of 0.5 root 2, and then the hypotenuse, the square root of 108.4 dec. So this is what that looks like right here. So given that it's all perfect, and we have the 15-degree line, 15, 30, 45, so half of that is a 7.5 degree section. So the angle here, theta, inside of this triangle is 7.5 or 7.6 degrees in base 12. So we've now confirmed that all of that works out. That's a perfectly balanced geometric structure that we've reached by analyzing the geometry contained within the lengths of the dodecagon, its relationship to the 45-degree line and the 30-degree line. We've gone through all the steps that we took to get to that point. Now we're just going to step back into the world of base 10. It's all base 12, obviously. And we're going to analyze this triangle that we just created from a base 10 point of view. So it has a base of 3 and 2/12, right? 3.2 in base 12, and then 5/12 for our 0.5 root 2. So because we're in units of square root of 2, we can basically cancel those out, and we just have the raw proportions of 3 and 2/12 and 5/12. So we're going to look at this from a trigonometric point of view. We're going to look at, SOHCAHTOA and trigonometry and find the arctan of theta. We're going to divide opposite over the adjacent lengths and see what the answer is when we do that equation. All right, so it's a pretty easy calculation to make with our base 10 calculator. We simply divide 5 by 12 and 3 and 2/12 by 12. We get this decimal place, 0.41666 repeating, and then 3.1666 repeating. So we divide the top by the bottom, we get an answer of 0.13157889. That number goes on. So we punch that into the calculator, we hit our arctan, and we get an answer of 7.49, and there's a whole bunch more digits. That's our angle. So 7.49 is not 7.5, which is the base 10 equivalent of 7.6 degrees in base 12, 7.5. So we've discovered that when we take that exact same proportioned triangle and convert it into base 10 measurements and then do our calculation, we realize that theta doesn't equal 7.5 degrees. So now we have to ask ourselves the question, which answer is more precise when we are looking at the geometry of this pattern? Is this pattern perfectly symmetrical, or is there something that we missed in its creation? Or is this answer a little bit off when we go through the procedure, the mathematical process of coming up with that number? So I'm going to be honest, I don't know what my calculator is doing when I'm hitting those buttons, arctan. I don't know what that process is, but I can see what the answer is, and I'm not sure that the mistake is on this side of the calculation as opposed to this side. I'm just going to take our little base 10, base 12, Dozenal decimal conversion stick here and just look at the numbers that we were forced to plug in because we're in base 12. We wanted to find the length of 5/12ths. So on our base 12 side, we count up 1, 2, 3, 4. There's 5/12. So we see where it lines up on the base 10 side. 1, 2, 3, 4. There's still some distance to go. So we divide this section by 10. We go one section. If we go 2, it's too far. So 1. Then that next little square we divide into tenths. And we go the distance of 0.6. Still haven't reached that same precise length. So we divide that little square into tenths, go another 6, and so on. So that's the process that we use to get that number, never reaching completely the precise length of 5/12ths because we're in base 10. We do the same thing with this slide. So this side. So using two numbers that are very close but not precise, we get an answer that is very close but not precisely the same as 7.5 degrees. So this is why this is so important, because I've come to the conclusion that this is the more precise and correct answer to that whole geometric process, is that here we've created a polygon that is anchored on the base 12 Cartesian plane defined by specific points that are all divided in by 12s, and it's precise and perfect, and that these angles are indeed 7.5 degrees. So I'm just going to collect my thoughts for a second and then share with you where this diagram takes us once we've confirmed in our minds and mathematically that this is a precise and perfectly symmetrical, balanced geometric pattern. Okay, that's the end of the 4th video in the series. You can now proceed to part 5.